So, have you ever thought about how scientists measure something that, well, something that never really ends? It sounds impossible, right? Today, we're diving into radioactive decay and this really clever idea called half-life that scientists came up with to solve that exact puzzle. Let's get into it.
All right, so here's the fundamental problem scientists were up against. They could see that radioactive stuff loses its radioactivity over time, but trying to nail down how long the whole process takes, that was a serious challenge.
The basic principle is super simple. You've got a sample with unstable atoms. As those atoms decay, the sample as a whole gives off less radiation. So the older it gets, the less radioactive it is. Makes sense, right?
But here's where it gets weird. See, the decay rate isn't constant. It slows down as you have fewer and fewer radioactive atoms left to decay. So in theory, the radioactivity never actually hits zero. It just gets infinitely smaller, always approaching zero but never quite getting there. How in the world do you measure a total lifespan for that?
Well, to get around this, scientists came up with just a brilliant solution. They thought, okay, if we can't measure the whole thing, let's just measure how long it takes for half of it to go away. And just like that, the concept of half-life was born.
This visual explains it perfectly. So you start with a box full of radioactive atoms. After one half-life passes, boom, half of them are gone. But here's the key part. After a second half-life, you don't lose the other half. You lose half of what was left. And that process just keeps going, halving and halving again.
So if we're going by the book, that's the definition. Half-life is just a measurement of time. It's the specific amount of time needed for exactly 1/2 of the radioactive atoms you have right now to break down and decay.
And, this is really just two sides of the same coin, because as half the atoms decay, the amount of radiation they're putting out, what we call the activity or the count rate, that also gets cut in half. Same process, just a different way of looking at it.
Now you've got to understand, half-life isn't some universal number, not at all. Every single radioactive element has its own unique half-life. And the range is just staggering. We're talking from tiny fractions of a second to literally billions of years.
This lays it out really clearly. If something has a short half-life, it means its atoms are super unstable. They decay really, really fast, and so the radioactivity just nosedives. But if it has a long half-life, its atoms are much more stable. They decay slowly, so the radioactivity level drops at a much, much gentler pace.
I just love this description. Thinking of these long half-life atoms as basically unstable but kind of biding their time, it's perfect. It's like they know they have to decay eventually, but they are in absolutely no hurry to do it.
So, why do we care so much about this? Well, it turns out that this single property, how quickly or slowly something decays, has huge real-world consequences. It completely dictates how we can use these materials for everything from powering our cities to healing the sick.
Okay, first up, let's take a look at something with a really, really long half-life. I'm talking about uranium-235, which I'm sure you've heard of.
This stuff is the go-to fuel for nuclear power plants. And why? Because it decays so incredibly slowly, which gives you a steady, predictable, and very long-lasting source of energy. Perfect for what you need.
So how long is its half-life? Brace yourself, it's 700 million years. Yeah, that's what biding their time means. In 700 million years, if you have a chunk of it, half of it will still be there. Just incredible.
All right, now let's completely flip the script and look at the total opposite, an isotope with a super short half-life.
In medicine, they use materials like iodine-118 for things like medical scans. And here, you want the exact opposite of uranium, right? You need something that does its job quickly and then gets out of the patient's system as fast as humanly possible.
And that's really the whole ballgame. Uranium's long half-life is perfect for providing sustained energy. Iodine's short half-life is perfect for giving a quick diagnostic dose that won't expose a patient to radiation for a long time. The specific job determines the kind of half-life you need. Which kind of leads us to this final big question. We've seen how that 700 million year half-life is useful for making energy. But what about the waste? It means that waste stays dangerously radioactive for an almost incomprehensible amount of time. The very thing that makes it so useful is also what makes it such a massive long-term challenge. It really makes you think, doesn't it?